Welcome back to our course on networking and distributed systems. This will be lesson 7. Let's pick up where we left off. As we discussed earlier, end systems connect to the internet via an access ISP. The access ISP can provide either wired or wireless connectivity using an array of access technologies including DSL, cable, fiber, Wi-Fi, and even cellular. The ISP can be your telephone company or your cable company. It can also be the university or business organization. However, in order for a host to connect to the internet, the access ISPs themselves must be interconnected. Connecting those access ISPs together is often referred to as the network of networks. So if somebody asks you what's another term for the internet, it's a network of networks. In order to become what we know of as the internet, not only must the ISP be connected, all hosts on those ISPs must have access to one another. This results in a very complex structure. How can such a large group of hosts be joined? One way to do it would be to have each access ISP directly connect with every other access ISP. Such a mesh design is, of course, much too costly for the access ISPs, as it would require each access ISP to have a separate communication link to each of the hundreds of thousands of other access ISPs all over the world. This would just not be a good option. Another option is to interconnect all the access ISPs with a single global transit ISP. This global transit ISP would be a network of routers and communication links that not only spans the globe, but also have at least one router near each of the hundreds of thousands of access ISPs. This would all be expensive for the global ISP to build such an extensive network. To be profitable, it would have to charge each of the access ISPs for connectivity with the pricing based on the amount of traffic the access ISP exchanges with the global ISP. Now, if some company actually builds and operates a global transit ISP that is profitable, then other companies will build their own global transit ISP. This leads to another structure which consists of hundreds of thousands of access ISPs and multiple global transit ISPs. The access ISPs certainly prefer this second structure since they can now choose among the competing global transit providers as a function of their pricing and services. Note, however, that the global transit ISPs themselves must interconnect. Otherwise, access ISPs connected to one of the global transit providers would not be able to communicate with the access ISPs connected to the other global transit providers. The network structure just described is a two-tier hierarchy with global transit providers residing at the top tier like ISP A, B, and C tier, and access ISPs at the bottom tier. This assumes that the global transit ISPs are not only capable of getting close to each other and every access ISP, but also find it economically desirable to do so. In reality, although some ISPs do have impressive global coverage and do connect with many access ISPs, no ISP has presence in each and every city in the world. Instead, in any given region, there may be a regional ISP to which the access ISPs in the region connect. Each regional ISP then connects to Tier 1 ISPs. There are approximately a dozen Tier 1 ISPs, including Level 3 Communications, AT&T, Sprint, and NTT. There are multiple competing Tier 1 ISPs, and there may be multiple competing regional ISPs in a region. In such a hierarchy, each access ISP pays the regional ISP to which it connects, and each regional ISP pays the Tier 1 ISP to which it connects. An access ISP can also directly connect to a Tier 1 ISP, in which case it pays the Tier 1 ISP. So it is possible for an access ISP to just skip the regional ISPs and connect directly to the Tier 1 ISP. To complicate matters in some regions, there may be a larger regional ISP, possibly spanning an entire country, to which the smaller regional ISPs in that region connect. The larger regional ISP then connects to a Tier 1 ISP. For example, in China, there are access ISPs in each city, which connects to the provincial ISPs, which in turn connect to the national ISPs, which finally connect to Tier 1 ISPs. This is referred to as MultiTier Hierarchy. To build a network that more closely resembles today's internet, we must add some points of presence, multi-homing, peering, and internet exchange points to the structure. POPs exists in all levels of the hierarchy, except for the bottom, access ISP level. A POP is simply a group of one or more routers at the same location in the provider's network where customer ISPs can connect into provider ISPs. For a customer network to connect to a provider POP, it can lease a high-speed link from a third-party telecommunications provider to directly connect one of its routers to a router at the POP. Any ISP, except for Tier 1 ISPs, may choose to multi-home. Multi-home means that it can connect to two or more provider ISPs. So, for example, an ISP may multi-home with two regional ISPs, or it may multi-home with two regional ISPs and also a Tier 1 ISP. Similarly, a regional ISP may multi-home with multiple Tier 1 ISPs. When an ISP multi-homes, it can continue to send and receive packets into the internet even if one of its providers has a failure, and in hurricane-prone areas, for example. That's not a bad idea. A third party can create an internet exchange point, typically a standalone building with its own switches, which is a meeting point where multiple ISPs can peer together. To add to the internet structure, we can add content provider networks. Google is currently one of the leading examples of such a content provider network. It is estimated that Google has 30 to 50 data centers distributed all across North America, Europe, Asia, South America, and Australia. Some of these data centers house over 100,000 servers. The Google data centers are all interconnected via Google's private TCP/IP network, which spans the entire globe, but is nevertheless separate from the public internet. Importantly, the Google private network only carries traffic to and from Google servers. Google private network attempts to bypass the upper tiers of the internet by peering settlement-free with lower tier ISPs, either by directly connecting with them or by connecting with them at an internet exchange point. However, because many access ISPs can still be reached by transmitting through the Tier 1 networks, the Google network also connects to Tier 1 ISPs and pays those ISPs for traffic exchanges with them. By creating its own network, a content provider not only reduces its payments to upper tier ISPs, but also has greater control of how its services are ultimately delivered to end users. In summary, today's internet, a network of networks, is complex, consisting of a dozen or so Tier 1 ISPs and hundreds of thousands of lower tier ISPs. The ISPs are diverse in their coverage, with some spanning multiple continents and oceans, and others limited to a narrow geographical region. The lower tier ISPs connect to the higher tier ISPs, and the higher tier ISPs interconnect with one another. Users and content providers are customers of the lower tier ISPs, and lower tier ISPs are customers of higher tier ISPs. In recent years, major content providers have also created their own networks and connect directly into lower tier ISPs where possible. Here's a graphic showing you some of the regional ISPs and access ISPs. There's a point of presence from to and from the backbone, with routers going to and from the customer. A packet starts in a host, passes through a series of routers, and eventually arrives at another host. That was the end of the topic on ISPs. And so rather than start a new topic right in the middle or toward the end of one of them, let's just go ahead and take a break now. Take care of any assignments that you have pending. And when you're ready to go, we'll come back for the next section, which is talking about sources of packet delay.